So let us begin our today's session. So before that, do you have any queries regarding quadratic forms, matrices, etc. of linear algebra? And I have given one assignment in the Telegram group, so which comprises all the models of the topics which we discussed in matrices. So by taking 1 week of time, you please solve that assignment. As and when you have a doubt, I will give the approach how to solve it. Okay? Let us begin our today's session. Which is vector spaces. So before going to start this part, I just want to give some introduction of algebra. Which is useful to understand the concept of vector spaces. Exactly. Using augmented matrix method, our prime aim is to bring the eigenvalues in the diagonal place. That's it. Right. Obviously, they will come if you apply the same conjugate operations. The eigenvalues will come on the diagonal usually. Right. So without being confused, just assume that we are reducing it into a diagonal matrix. Then automatically eigenvalues will come on the diagonal. Right. So let us take some introduction of algebra. So before that, just consider the set integers. So first of all, let us have a discussion on the number system and its properties. Then slightly we move into the concept of vector spaces, because it is in the earlier stage it looks like somewhat theoretical. Slowly it totally converts into problematic, right? Suppose let us take the operation addition. Usually we have 4 arithmetic operations: addition, subtraction, multiplication and division. Let me say, if I have taken 2 numbers a, b, which are integers, if I add them, is the result an integer or not? Yes or no? Right. So this property we call it as closure law or closure property. The point which we need to observe here is, you have taken a set Z which consists of all the integers. There you have taken 2 values or 2 numbers a and b. If you perform an operation, the result will belong to the same set. So please understand, this property will not hold always. For example, if you take natural numbers, take the operation minus. If you take any 2 natural numbers, if you subtract them, is it a natural number? Yes or no? Not always, because if you take a as 2 and b as 3, the difference is -1, which does not belong to the natural numbers. Accepted? So if you take A as 3 and B as 2, the difference is 1, which is a natural number. Agreed? So please understand the concept of closure law. You have taken a set, you are taking one operation, say plus. Whenever you take any two values, if you apply the operation, the result must belong to the same set. This is the concept of closure law. I have taken one example which closure law holds. I have taken another example where closure law does not hold always. Okay? Any more confusion to anyone? Please tell. Now, again in the integer set, you take three values A, B, C. You can add them in either the way. Whatever the way you add, the result is same. So this property is called associative. So did you come across these properties earlier or not? If not, please take a note of them. However, we are not using these properties while solving the problems, but these are important in understanding the context of vector spaces. Okay. Fine. Now, the other property I am going to say is identity. Identity means you take any integer. Can you find an integer such that after adding it, I should get the same value? What is the value there? X plus something again will give us X. What is that number? 0, right? Is 0 an integer or not? It is an integer. So 0 is called identity. The element 0 is called identity. And one property is inverse. It means that whenever you take an integer x, after adding what value, you should get identity. So if I have taken 5, the integer value, what is the corresponding inverse I should take? Minus 5. Minus 5 is also an integer, so it will belong to the same set Z. It is called inverse property, right? So, and the last one I want to say is commutative. So whenever you take integers to x plus y is equal to y plus x, it always will hold. It is called commutative property or abelian property. Why I am stating about these things is, in number system, you have integers, rational numbers, real numbers, complex numbers. So in which there is a set or there are some sets, by taking two operations at a time, plus and dot, they will satisfy all the 5 properties: closure, associative, identity, inverse, commutative. With respect to addition and with respect to multiplication, those sets will satisfy all the 5 properties. They will called as field. The example is real number system is a field. Complex number system is a field. Similarly, rational number system is a field. Okay. So these are some properties related to the number system. Any questions to anyone? So just here you understand that whenever you take a set, you are going to check the properties closure, associative, identity, inverse and commutative with respect to an operation. That may be plus, that may be minus, that may be multiplication, etc., etc. Whenever a set satisfies these properties with respect to plus and dot both, then we call it as a field. Any confusion to anyone? Please tell. No, I am going to give the definition of vector spaces. Now, you take a set V. The elements in V are called vectors. So, in the set, you can take numbers, you can take matrices, you can take functions, you can take polynomials, whatever the case may be. You can take anything in this set. The elements in this set, I am calling it as vectors. Now, I will take a field. So usually you have three fields, either rational numbers or real numbers or complex numbers. You consider any field. Now, comparing the elements over these two, I will check whether some properties are satisfied or not. So, on the set V, I will take the operation plus and I will check that V comma plus is an abelian group or not. So what is meant by an abelian group? It is satisfying the five properties as I mentioned earlier: closure, associative, identity, inverse and commutative. Let me say, if I take that V contains numbers, here plus means numbers addition. Let me say V contains matrices, plus means matrix addition. If V contains polynomials, plus means polynomial addition. So depending upon the element here, plus indicates the corresponding property, and I am saying that all these five properties are satisfied by plus over the set V. Okay? Is it clear? Right. Now, I am taking another operation dot called as scalar multiplication. There, I call plus as vector addition. Why I am calling it as vector addition? Because the elements in the set V, I am calling them as vectors. Since I am adding them, I am calling it as vector addition. Right? Now, with respect to this dot, I am checking the following properties. The properties are Usually, the vectors in V are denoted with the symbols alpha, beta. And generally, we denote the numbers with A, B, C, etc. You can denote with A1, A2, A2 also. So, A, B symbols are generally used for numbers notation. Alpha, beta generally used for vectors notation. If I say alpha, beta belongs to V means alpha, comma, beta are vectors. If I say A, comma, B belongs to F means A, comma, B are numbers. They may be real numbers or complex numbers or rational numbers, whatever they may be, right? So, these four properties must be satisfied by both V and F. I can take any two vectors here, I can take any numbers here. They together constitute these four properties. So, in total, I am checking for 9 properties. These are 4 and these are 5, total 9 properties. If they are satisfied by both of these sets, then I say that V of F is a vector space, or V is a vector space over F. Symbolically, I say that V of F is a vector space. So, in general, if I have written that V of Q is a vector space, V is a set containing vectors, I am taking numbers as rational numbers. So, I am checking these properties where A, comma, B are rational numbers. If I have written V of C, I have taken the numbers or scalars as complex numbers. V contains the vectors as usual. It may be polynomials, matrices, whatever the case may be. Okay? Is it clear? So, vector space means satisfying 9 properties. These are defined in this way. Now, as usual, at the +2 level, you have studied that vector means a physical quantity which has two properties, magnitude and direction. If you apply the thing to coordinate geometry, a ray starting from origin and passing through a fixed point in the space, accepted? That we generally treat it as a vector. Yes or no? Right. Now, this theory deals with all the vectors we have learned at the level of coordinate geometry or three-dimensional geometry, what you call. So, if you take two-dimensional geometry, let me say this is a vector. Suppose it passes through the point 1, 2. So, there for that vector you have a vector notation. Here in vector spaces, this vector or this ray will be typically identified or assimilated by the point itself. If I write alpha is equal to 1, 2 means it is a vector in the two-dimensional geometry passing through the point 1, 2. If I have written that beta is equal to 1, 2, minus 3, so it is a vector in the three-dimensional geometry whose coordinates are 1, 2, minus 3. So typically the vector is identified by means of a point here. There is no need of visualization, the ray starting from origin and passing through a fixed direction. So by default it is taken here, right? So you simply understand that vector is nothing but a point here taken in n coordinates. You will take 2-dimensional, 3-dimensional, 4-dimensional and n-dimensional, so on. Let me say I have taken two vectors, beta 1 and beta 2 is equal to, and I am going to add them. So how I am going to add them? First value plus first, second plus x, third plus third. So 2, 1, 2, this is the result. So this is called vector addition. So you can extend this property to n number of coordinates, 2-dimensional, 3-dimensional, 4-dimensional and n-dimensional. Clear? And scalar multiplication means you take any number and multiply the vector with that scalar. Let me say I have taken a is equal to 6 and I took a vector alpha is equal to 1, 2, 4, minus 3. This is a vector having 4 coordinates. It is a 4D vector. And scalar multiplication means a alpha. A vector is multiplied with a number. So this is the number and this is the vector. So vector is multiplied with a number. Another name for number is scalar. That's why we are calling it as scalar multiplication. And how it will be? 6, 1, 6, 12, 24, minus 18. This is the answer. So if you talk of regular vectors, it is just like dealing with numbers. If you apply the theory to abstract level, so you can take matrices, polynomials, functions, anything, the same thing will follow. Clear? So if I take V contains functions, vector addition means adding up of functions. If I say that V contains all 2 by 2 square matrices, vector addition is nothing but addition of 2 matrices. And scalar multiplication means I am multiplying a matrix with a number. That is the whole idea behind the vector spaces. And you are saying that if it is a vector space, then it satisfies all the 9 properties which are stated earlier. And one thing is, if I have said that M 2 by 2 of R is a vector space, it means that M stands for matrices. I have taken all square matrices of order 2 by 2 over the real number system R. It is a vector space. So what does it mean? If you take the 2 by 2 matrices, they will satisfy the 5 properties: closure, associative, identity, inverse, and commutative with respect to matrix addition. And the 4 properties are there. So those 4 properties are satisfied by you take a number, you take a matrix, multiply them. It is called scalar multiplication there. So if I have written that V of C is a vector space where V contains all continuous functions from closure interval 0, 1 to R. So here C stands for the complex numbers. So scalars are nothing but complex numbers. And in the set V, I am taking all continuous functions from closure interval 0, 1 to R. So usually, while dealing with our vector spaces problems, we stick on our discussion only with these vectors, the numbers concept only. Occasionally, we do some problems based on that matrices, functions, polynomials, etc. So this is the context of vector spaces, the definition part. Is that clear, or do you have any confusion with regard to the definition? Right. Now, let us take some other definitions. So in this class, I am going to give the list of definitions first. Then we go with the next level. Once you understand the fundamentals thoroughly, problem solving is just like a cakewalk. You love the problem solving. It's very easy. So subspace. Suppose you take a vector space V of F and you take a subset in it, say W. We say that W is subspace of V if W itself a vector space. So subspace, if you understand the word, you can bifurcate like this. Subset and vector space, we call it as a subspace. So for every vector space V of f, always there will be two subspaces. One is the zero vector space and the other one is V itself, because V is a subset to V itself. So these two are called trivial or improper subspaces. So if you take any subset which is bigger than 0 and smaller than V, this is called proper subspace or non-trivial subspace. Okay. Now what happens, I have a vector space with me and I have given a subset to you. Now the thing is, I want to know whether it becomes a subspace of the vector space or not. Now for this, I need to check all the 9 properties which are given earlier, which is very difficult to do always. I have a set, every time I am going to check that all the elements in the set are satisfying the 9 conditions stated earlier, which is difficult. So to avoid that, some checking conditions or test conditions are given. So they are called as necessary and sufficient conditions. It is just like implies and implied by condition, if and only if condition. So what does it mean? I have given a vector space and I have taken a subset of it. I just want to know whether it is a subspace or not. So for this, the subset W must satisfy one of these tests. So what are they? First one is this is the first test. I need to verify two conditions, that whenever I take any two vectors in the subset, then the difference between them, alpha minus beta, must belong to W. And the second condition there I need to check is, I can take any vector, I can take any number, the scalar multiplication A alpha must belong to W. If these two conditions are satisfied by W, then we say that W is a subspace of V. Now, the second test comes into existence, that since I am little lazy to check for the two conditions, I just want to check for one condition. So the condition is nothing but, you can take any two numbers, you can take any two vectors, then A alpha plus B beta must belong to W, where alpha beta are any vectors in the subset W, because you are checking for W, and A comma B are any scalars in the field F. So the result A alpha plus B beta must belong to W. Then we say that W is a subspace of the vector space V. Okay. So whenever a question is given that verify whether W is a subspace or not, you are going to make use of this single condition or the two conditions given here. Suppose you are checking with these two conditions. If first condition is satisfied, second condition is not satisfied, then it is not a subspace. So the two conditions are valid conditions, two must be satisfied by W. Okay. So please take a note of this. Then I just want to give some sample hints for you so that you can understand what it is actually. By doing the examples, you can say that. Please tell after noting. And if you have any doubts with regard to these definitions, you can ask. right? So for your visualization, you just understand that you take all the 3D space. X, Y, Z, origin. So this is entire 3D space. You treat it as a vector space. It is nothing but just like consisting of all points. Don't imagine that rays are coming from origin to different directions. Don't imagine like that. Set of all points here. This is the vector space. So what is meant by subspace here? A plane is a subspace here. So you know what is meant by a plane equation, right? Is it a plane equation or not? So which passes through the origin? So any plane passing through the origin is a subspace in the vector space of three-dimensional space, or cube. You can call it as R cube. So let us generalize this. So whenever I have written a plane equation, Px plus Qy plus Rz equal to 0, where P, Q, R are some numbers. You can say the field F. Then always this plane is a subspace. So I want to prove that every plane in the three-dimensional space is a subspace of it, which passing through the origin. Is that clear? Yes or no? If the context is clear, I go with the solution part. Right. Now, suppose this is a plane. What is the checking condition for subspace? I can make use of the test 1 or test 2. Suppose I want to make use of test 2. So what is the condition there? A alpha plus B beta must belong to W. It means that if you feel that this is W, A alpha plus B beta must belong to this. So we are going to prove that A alpha plus B beta must belong to that plane. So what are alpha beta and what are AB there? A comma B are any numbers, alpha comma beta are any vectors. So here vectors means, since you are taking a three-dimensional space, alpha and beta are nothing but any two 3D vectors which are in W. So in this definition, what you are proving, you can take any two numbers in the field, you can take any two vectors in W, then you should say that A alpha plus B beta belongs to W. So here also, I will take any two numbers in the field F, and I will take any two vectors, alpha is equal to x1, y1, z1, and beta is equal to x2, y2, z2 in the plane. Let me say this is 1. Now I have to prove that A alpha plus B beta belongs to 1. Please understand that alpha belong to this plane means what? Alpha is a point which satisfies the plane equation. In other words, alpha lies on the plane. Similarly, beta belongs to the plane means beta is a point which satisfies the plane equation. So if I want to prove that A alpha plus B beta belongs to the plane means A alpha plus B beta must satisfy the plane equation. Accepted? Did you get the logic? All of you. Right. So let us go for it. So it is nothing but A into x1, y1, z1 plus B into x2, y2, z2. A alpha plus B beta means this. So if you add them, it is nothing but ax1 plus bx2, comma, ay1 plus by2, comma, az1 plus bz2. This is a point. I have to show that this point satisfies the plane equation. So in place of x, y, z, I am to substitute these coordinates and I should get the result as 0. So if I have applied that, so P into ax1 plus bx2 plus q into ay1 plus by2 plus r into az1 plus bz2 equal to 0. I need to consider this. I should prove the result is 0. So you can multiply all the values and you can take common. So if you take a as common, it is nothing but px1 plus qy1 plus rz1 plus b into px2 plus qy2 plus rz2. So this is nothing but a into 0 plus b into 0. Because x1, y1, z1 is a point on this plane, so it satisfies the plane equation, hence it is 0. Since x2, y2, z2 is a point on this plane, it satisfies the plane equation, hence this value is 0. So a dot 0 plus b dot 0, the result is 0. Therefore, this point a alpha plus b beta is lying on the plane, hence this plane is a subspace. Clear? Any doubts you can ask? I think from the definition perspective and the necessary and sufficient perspective, you understood how to proceed with a problem, how to prove that it is a subspace. Exactly, you can prove a alpha plus b beta condition, or the first two conditions I have stated, that's it. Any one test you are checking, two tests are available for us. You can make use of test 1 or test 2, anything you can make use of it. Exactly. So every plane passing through the origin is a subspace. So you take, let me say, the simple thing as, let us take that this is 6, px plus qa plus rz equal to 6. Now you take 2 points which are satisfied by that. Now you are going to say that a alpha plus b beta also lie in the same plane. If you find at least one point which does not satisfy, then it's okay. It is not a subspace. That's it. So actually, we are talking about the identity, right? So here, origin is the identity. The point origin is the identity. So every subspace, every vector space will contain the identity. So if a plane passes through the origin, means it contains the identity. So it is a subspace. If it does not passes through the origin, means it is not a subspace. Exactly. Vector space earlier is very similar to abstract algebra in the beginning. Later, it is totally problematic approach. For the first two classes, you are going to learn some definitions. Later, everything is just like problematic. There is no theory at all. With regard to theory is there, theorems are there, but you are not learning them with regard to UPSC point of view. They are not, what you call it, you can say that they are not necessary to learn. That's it. So is this concept clear to you all? Fine. So suppose if you talk of 2D space, two-dimensional geometry, x-axis and y-axis. So what is the subspace here? Any line passing through origin. Any line passing through origin is a subspace. You can check for that. You can take y is equal to 2x, 3x, 4x, anything. You can take like that. Now you take a point, you can take any 2 points, you can take any 2 numbers. Then if you calculate, it will come in the form of y is equal to mx. It will satisfy the line equation y is equal to mx. So any line passing through the origin is a subspace if you take two-dimensional space. Now the question comes that for two-dimensional it is okay, for three-dimensional it is okay, what about four-dimensional? So there you cannot visualize actually, right? So in this way it comes as abstract. So take 5-dimensional, 6-dimensional, n-dimensional. Whatever the case may be, if A alpha plus B beta is satisfied, it is a subspace, otherwise not. Okay? So the geometrical perspective is a limited one. Up to some extent it is okay. After that you cannot visualize the things. You need to understand the theory only. Fine? Okay. Now let us take that. Suppose you consider field is equal to real numbers, vector space is equal to R cube, nothing but 3D space. Now I have given a set W is equal to set of all x, y, z such that x, y, z are rational numbers. Now the question is W a subspace of V? So you take that field is real numbers. The vector space I have taken as the 3D space x, y, z system, and in x, y, z system I am taking the points such that whose coordinates are real numbers. My question is, if I have taken all those points into one set, is it a subspace or not? So is the question tag clear? Any doubts? Yes or no? So please let me know if you have any doubts with regard to these fundamentals. Don't hesitate to ask. If I am going fast, please stop me. Is everyone clear with the question tag, what it is asked and the objective of the question part? Fine. Now, if I am able to use test 1 or test 2, whatever it is, if the test is completely satisfied, W, the set of those points, is a subspace of R cube. If the test is not at all satisfied, then it is not a subspace. So in this case, it is not a subspace. You can take a counter example of it. So here, W contains all the 3D points where the coefficients are rational numbers, right? So you take a thing that 1, 3, 5, this belongs to W. Now if you want to make use of test 1, what is test 1? Whenever I take two vectors, the difference must always belong to W. This condition will be satisfied by W trivially, because whenever you take a 3D point, you take another 3D point, the coordinates are nothing but rational numbers. If you subtract them, rational number minus rational number, always it is a rational number. You cannot get a different one. So first property will be satisfied by W automatically. So let us go with the second property, that is scalar multiplication. So what is meant by scalar multiplication? In the set W, you take any vector as you wish, and you take any scalar in the field. Whatever the field is given to you, you take any scalar in the field. So if you multiply that, the result must belong to W. That is called scalar multiplication or second condition. So here what happens, I will take the scalar A is equal to root 5. I will take the vector alpha is equal to 1, 3, 5. Now if I apply scalar multiplication A alpha, it is nothing but root 5, 3 root 5, 5 root 5. Accepted? So is that result belong to W? So W is not a subspace here. So among the two conditions, first condition alpha minus beta is satisfied, second condition is not at all satisfied, so W is not a subspace. Now you can understand that. How to prove a subspace and how to prove it is not a subspace. You can do the same thing with A alpha plus B beta also, but while proving that it is not a subspace, it is convenient to check for the two condition system. If you are going to prove that it is a subspace, go with single condition method A alpha plus B beta. That's it. Okay? Any questions or doubts to anyone? Fine. Now, for your convenience, I just want to take one more thing for your discussion part. Suppose you take the 3D system. Again, consider x-axis, y-axis, z-axis. In this 3D system, you will have xy plane, you will have yz plane, and you will have zx plane. My question is xy plane a subspace or not? So if you want to say that it is a subspace, you should verify the condition A alpha plus B beta or the two conditions, whatever it is. Now, what is the pattern of xy plane? It contains x coordinate, y coordinate, and z coordinate is 0. Accepted? So, if you want to write the points on xy plane, how do we write? So it contains all 3D points where x coordinate is present, y coordinate is present, z coordinate is 0, and xy coordinates are nothing but real numbers. This is the definition of xy plane. Accepted? Right. So if I want to say that it is a subspace, you take any two numbers, you take any two vectors. If you calculate A alpha plus B beta, the result must be in this form. So you take alpha is equal to any point x1, y1, 0, beta is equal to any point x2, y2, 0, and you take any two numbers a comma b which are real numbers because the number field is nothing but real numbers. So if you consider A alpha plus B beta, it will come like this. Now see, this is a real number. This is a real number. So it belongs to the same form. So this belongs to xy. Therefore, xy is a subspace. Similarly, yz plane is a subspace. Similarly, zx plane is also a subspace. So if you want to check whether a plane is a subspace or not, we do like this. Is it okay? So will it give you the clear idea for the subspaces concept and vector space concept to all of you? Still you have any other doubts? Do you have any doubts? Right. Now let us move somewhat different. Let us take the other definitions now. You take a vector space V of f. Now in this, I took some vectors, say alpha, beta, gamma. Now I am doing the thing that number into vector, number into vector, number into vector, just like A alpha plus B beta. So if you simplify that, you will get a vector as a result. Accepted? So this type of notation we call it as linear combination. So if you generalize that, you take a set of n vectors, alpha 1, alpha 2, so on, alpha n in the vector space V of f. And you take any scalars in the field a1, a2, so on, an, which are scalars in the field f. Now, the sum of the products a1 alpha 1 plus a2 alpha 2 plus so on plus an alpha n will belong to the vector space V of f, because this is a vector, because you are multiplying a vector with a number. So this is a vector, this is a vector, this is a vector. If you add all these vectors, the result is nothing but a vector. So this type of notation is called linear combination. So what is meant by linear combination? The sum of the products a1 alpha 1 plus so on plus an alpha n is called a linear combination, where a1, a2, so on, an are scalars taken in the field f, alpha 1, alpha 2, so on, alpha n are vectors taken in the vector space V. Okay. Now the question is, how many linear combinations will exist? The term linear combination is typical because if you take alpha 1, alpha 2 as 2D vectors, then you are going to get as a line. This simplification is nothing but a line. So linear combination gives a line geometrically. That's why the very word is given as linear combination. Okay. The significance of putting the name is that linear combination. So if you simplify this expression, it is going to give us a line. Now the thing is, let us fix that alpha 1 is equal to say 1 0 0, alpha 2 is equal to 0 2 3, and alpha 3 is equal to 1 0 1. These are three vectors. Now I can take any three scalars in the field. So I am going to calculate a1 alpha 1 plus a2 alpha 2 plus a3 alpha 3. Now what happens? If I take a1, a2, a3 as 1 1 1, I will get a vector here. If I take a1, a2, a3 as 0 0 0, I will get the 0 vector here. If I take a1 is equal to 1, a2 is equal to 1, a3 is equal to 0, I will get another vector here. Now what is happening? I have fixed the vectors, but I am changing the scalars here. I can take all possible scalars in the field f. Now what happens? You will get a set of vectors here. If you put all these vectors together, you will get a line. That's why we are calling it as a linear combination. Okay. So if you talk about linear combination, the vectors are fixed, scalars are not fixed. You can take any kind of scalars in the field f. Is it clear? And here, if you write all possible linear combinations with regard to a set, it is called linear span. It becomes a subspace. So for our convenience, just imagine like this. Suppose we have taken a plane in the 3D space. This plane is simply observed like this combination of lines. Either you take vertically or horizontally. If you put all lines together, it will become the whole space, the subspace. Accepted? Yes or no? So linear span is nothing but all possible linear combinations. So all possible lines, you say, that will constitute a subspace for us. Okay. So if you take a set S, all possible linear combinations using the elements of S is called linear span. Symbolically, we write it as L of S. I will just give one simple example to understand. Just go with 3D space again. Now, x-axis, the unit vector of it is nothing but 1, 0, 0. Accepted? Agreed or not agreed? The unit vector of x-axis. So for y-axis, it is nothing but 0, 1, 0. And for z-axis, it is nothing but 0, 0, 1. So, if you write the three vectors together, if you write all possible combinations, with this set, you will get whole 3D space. I will simply say like this. Let me say, I have taken, say, this thing as alpha 1, alpha 2, alpha 3. What is the linear combination? L of S is nothing but ABC are real numbers because we are talking about the 3D system. Now, if I take A is equal to 1, B is equal to 1, C is equal to 1 here, if you add up, you will get the point 1, 1, 1. Now, if I say that if I take A is equal to 1, B is equal to 2, C is equal to 3, I will get the point 1, 2, 3. So, if I take A is equal to 1, B is equal to minus 1, C is equal to minus 3, I will get the point 1, minus 1, minus 3. Now, what happens? Whatever the point you take in the whole 3D space, that is typically as a form of like this. So, the set 1, 0, 0, 0, 1, 0, 0, 0, 1 is a spanning set for the 3D space. So, actually in 2-dimensional geometry or 3-dimensional geometry, how do we learn about the point? If I say that the coordinates of the point are 1, 2, 3. So, on x-axis, its value is 1. On y-axis, its value is 2. On z-axis, its value is 3. Accepted? This how do we learn in solid geometry system? Agreed? Are you getting the thought? So, those values are nothing but ABC. In other words, you are projecting the point on the axis. So, the projecting axes are nothing but the vectors. The distance from origin to that part is nothing but the scalars A, B, C. They together constitute the linear combination. Okay? Are you getting the idea? The spanning set, linear combination, etc. So, I will wait for your understanding. Please take your time. Then we discuss further. So, did you get the idea of linear combination and linear span? So, if you take a set of vectors, whenever you write a combination, the vectors are fixed. While changing different scalars, you will get different vectors in that space. So, all those vectors are taken together into one set and we are calling it as the linear span. Right. So, if you talk about the 3D space, the vectors 1, 0, 0, 0, 1, 0, 0, 0, 1 are nothing but the spanning set for the whole 3D system. Let me say one good example for you. Without the geometrical interpretation, you can understand like this. Please understand, spanning sets are so many. You can have so many spanning sets. I took the generalized example. Suppose we have taken all 2 by 2 matrices or the real number system R. That means the entries in the matrix are nothing but real numbers. Now let us take a small example. Say this is a 2 by 2 matrix. Now if I have considered the 2 by 2 vector space, what is the spanning set for it? So I will say that this thing will be written as do you accept for it? Yes or no? All of you. So the spanning set is typically 1 0 0 0. So whatever the 2D matrix you take, right, then this is the spanning set, because using these 4 matrices, if you write a linear combination, the matrix whatever you take will come. Clear? Not only the combinations of ones and zeros, you can take other matrices too. It is possible to write such linear combinations. My intention is, I want to discuss the idea of linear combination, the sum of the products, number into vector, number into vector, number into vector is called a linear combination. The vectors what you are using here are called the spanning set, because they together constitute the whole space. Okay? Any more doubts for you? Let me take one more small example. Suppose we have taken a polynomial. X plus x square. Let me say I have taken the vector space V of f, all third degree polynomials or up to third degree polynomials. I am taking constant polynomials, I am taking first degree polynomials, I am taking second degree polynomials, and I am taking third degree polynomials. If I took all these polynomials into one set and if I call that as a vector space, then what is the spanning set for it? It is very simple. The spanning set is simply 1 x, x square, x cube. Because whatever the polynomial you consider, it is typically written using these things. Some number into 1 plus some number into x plus some number into x square plus some number into x cube. These numbers are taken in the field. So here for this polynomial you will write that 0 into 1 plus 1 into x plus 1 into x square plus 0 into x cube. So every polynomial can be written by using these things. So this is the spanning set for all these polynomials up to third degree. Okay? So still anybody has any more doubts with regard to this linear combination and spanning sets? Now let us do one problem which gives an idea. Shall I take the problem? Right? So if you are getting disinterest, please tell me. I will stop. Now the question is, represent the vector alpha is equal to 1 minus 2, 5 as a linear combination of represent the vector alpha is equal to 1 minus 2, 5 as a linear combination of 1, 1, 1, 1, 2, 3, 2 minus 1, 1. So let us do the problem. So we are going to write the vector alpha 1 minus 2, 5 as a combination of these three. So let us give names for convenience. Say this is x, this is y, this is z. So you have to write alpha is equal to some number into x plus some number into y plus some number into z. If it is possible to find the numbers, or if we have proved that the numbers are existed, then it is called a linear combination. Accepted? As per the definition concerned. So let us say alpha is equal to ax plus by plus cz, where ABC are numbers belong to the field F. Now my turn is I need to evaluate the values of ABC. So let us substitute the values. 1 minus 2, 5 is equal to a into 1, 1, 1 plus b into 1, 2, 3 plus c into 2 minus 1, 1. Simplify the RHS part. So multiplying and adding, you will get a plus b plus 2c, a plus 2b minus c, a plus 3b plus c. So if you equate them, a plus b plus 2c is equal to 1, a plus 2b minus c is equal to minus 2, a plus 3b plus c is equal to 5. Accepted? Please check. Now I request you to solve these equations. Give me the values of ABC for me. Take a minute of time and solve. You can solve it any method. Simply solving the equations, matrix method, substitution method, anything you know. You can substitute and you can apply and you can solve. So just give me the values of ABC to me. So if you say that minus 6, 3, 2, those values must be satisfied by all the three equations. Please understand, not by a single equation. Can you say that these values are satisfied by all the three equations? Check on that. So minus 6, 3, 2 are satisfied by all the three equations. Agreed? Right. So A is equal to minus 6, B is equal to 3, C is equal to 2. So you have written that alpha is equal to minus 6x plus 3y plus 2z. So you have found a linear combination. So it is possible to represent the vector alpha as a linear combination of the given three vectors. Okay? So any doubts for anyone? If you are clear, I just want to take one more problem, then I will wind up our today's discussion. In the next class we will meet. Now take the vector as 2 minus 5 3 and the values as 1 minus 3 2, 2 minus 4 minus 1 and 1 minus 5 7. So this is alpha I have given, and represent that vector as a combination of these three. So this is x, this is y, this is z. Let us take. So find the values of ABC for me and give back to me. Please go for it. So just write the linear combination, solve it for the values of ABC and give the reply. What is the solution of it? ABC values. Now for this problem I will say that you cannot solve the equations because there you will get two dependent equations. Right side values are different, left side coefficients are equal. You will get that on solving 0 is equal to something you will get. The equations will become dependent equations. The conclusion of the problem is it is not possible to find a linear combination for alpha with respect to xyz. So please go through it and give me the feedback. Check for it. Because finding linear combination is very important, because while going through the previous year questions you can find problems on finding linear combination. Are you with me? Did you get a similar kind of answer? Please go through that. So do you agree that the linear combination is not possible? Please respond everyone. So did you get any two dependent equations that such that coefficients are equal? Right side RHS will have different constraints like that, so that both equations gets cancelled. You will get an inequality. Or are you able to find the values of ABC such that combination is possible? So let us conclude our today's session here. We will meet in the next class. B and C will have two values. I can say that if you substitute those values, you should get the combination possible. I can say that you cannot get rid of the equations. Equations are not solvable there. I'll say that. So B minus C is equal to 1 by 5, right? What is the other equation with regard to B and C? Right? Now see, now what I am saying, you are going to eliminate one parameter. Whatever the thing you do, you will get 0 here, you will get some number here, right? That is absurd, which is not possible actually, correct? these two are dependent lines, they overlap. So combination is not possible. That's it. So you can do the other way, that you can represent the whole thing in a matrix form. The equations are nothing but, let me say, a plus 2b plus c is equal to 2, minus 3a minus 4b minus 5c is equal to minus 5, 2a minus b plus 7c is equal to 3. So if you write the respective matrix system, 1, 2, 1, minus 3, minus 4, minus 5, 2, minus 1, 7, or you can take the augmented matrix. So if you reduce that into echelon form, then what happens? This row completely becomes 0 and here you will get a number. So what happens? Rank of A is not equal to rank of A by B. It will become inconsistent. It has no solution. You can take like that. Okay? Are you getting the idea? You can apply the matrix technique or you can apply the regular equation solving technique. You can go for that also. Check for the echelon form. Fine. So for solving this, since this is a system of equations, you can go with the regular matrix solving, you can go for the echelon form, you can go for regular equation solving. Either the way you can find the values of ABC. Okay? So let us wind up our discussion here. Since you know how to find the values of ABC, thanks to all. If you have any other queries with regard to the discussion, you please ask for today's topic. The definition, basic ideology, subspaces, linear combination, problem solving techniques. Do you have any queries? You please ask. Otherwise, let us wind up here. We will meet in the next session. If anybody has any confusion with regard to the approach.